Okay. So yeah, hello everyone. My name is Minko Gechev. I'm a senior developer programs engineer in the Angular team at Google. As developer programs engineer, I have the opportunity to both attend events as the one today, talk to developers, collect some feedback, and later on build tools for them in order to solve problems that occurred, and work with our engineering team in order to improve the development experience of Angular. So one very frequent concern that I hear is building at scale. So today we're going to address this. I'm going to give you an overview of how we're building our JavaScript at Google. So pretty much this is going to be kind of a superset of the part of the talk that Stephen gave. We're going to focus particularly on our monorepo and Bazel, what Bazel is and how we're using it. So the agenda for today. Oh yeah, first disclaimer, I had coffee for the first time for the past 2 months. So if I speak very quickly, just let me know. So yeah, first we're going to focus on the evolution of the web and why do we actually need a build process. After that, we're going to take a look at our monorepo, Google 3. We're going to discuss how we're building applications at Google. This is not only about building JavaScript web apps. This is how we're building applications in general. And right after that, we're going to discuss some open source alternatives of the tools that we have been using internally and how you can implement them as part of your development process. So building a web application in 1991. It was a pretty easy process back then. Like we needed a text editor and a web server in order to preview the results. And that was fascinating. We had hyperlinks across different pages, hosted on the same server or different servers across the network. And well, that was a distributed system. That was fantastic, but it was also a little bit limited. Back then, we had HTML. We didn't have JavaScript or CSS. And at some point, in order to stay competitive, the web browsers, they decided to introduce some level of interactivity. And on the 5th of March, 1995, they decided to start developing JavaScript. Brendan Eich was the one who was responsible for doing that. And basically, that was going to shape the future of the web. About 9 days later, he was completed with the development of JavaScript. And we're kind of still trying to fix it today. Now the web platform has a bunch of network protocols. We have HTTP, WebSockets. We have TLS. We have different programming languages. In fact, HTML and CSS turn out to be Turing complete, so you can pretty much write any program by combining these two. But we also have JavaScript as well, which keeps evolving by introducing new features and fixing issues that occurred over the years. And we have a bunch of web APIs. All of this is so powerful that we can build desktop-like experiences. Building a web application in 2019 now is slightly more complicated because, well, developers want both. They want the convenience of web apps, and they also want the power of the desktop applications. So now in order to build a web app, we usually need to pick a programming language because, well, JavaScript is not ideal. And we often need a type system. After that, this language needs to be compiled, so we need a compiler. We need a framework often. We need to compile the assets of the framework. We eventually need to build everything together with a bundler. We have different test runners. We have assertion libraries, different CIs, and so on and so forth. So we need to scaffold everything. That's where the CLIs come in. And this complexity just keeps going on and on. In fact, not all the problems in an organization are technological, unfortunately. We also have people with different backgrounds who are used to build things differently. For example, we have people who are used to use make, the build tool make, and build their C++ projects, let's say this way, or even their JavaScript projects. We have people who are more used to the Java ecosystem, where they're using Maven or Gradle. We also have the JavaScript developers, where it's pretty much the Wild West. We have NPM scripts. We have different bundlers. We have a variety of different build tools. In the same time, everything needs to scale really well. Well, the faster the project grows, the slower the build time usually goes as well. And most of the tools out there in the JavaScript ecosystem, they're not built with scale in mind. Now let us look at an example from Google, and let's see how we can potentially try to build it with the state-of-the-art tooling in JavaScript. One of the biggest clients of Angular right now is the Google Cloud Console. This is a very high-level, probably a little bit inaccurate structural diagram of the individual pieces of the platform. We have Google Cloud on top, which has some user interface. It has a lot of backend services. The user interface is consuming Angular and also Angular material, and both of them depend on TypeScript. If you look at the UI, only the UI itself is, I think, 2 million lines of code is a little bit outdated. It is much more right now, but it's quite a lot of source code. If we want to build it with the state-of-the-art tooling in JavaScript currently, all we need to do is run npm install and eventually bundle everything together with a tool such as Webpack, which is a tool which basically has a pipeline that takes our source code, moves it to a compilation stage. After that, it goes through bundling, minification, and so on and so forth. So basically, Webpack is a bundler which tries to be a build system as well. And it is specifically implemented to work well with JavaScript and WebAssembly. If we try to build Google Cloud with Webpack, we're going to get something like this. We're going to get out of memory pretty quickly. And in order to work around it, we can potentially decompose the user interface into separate sublibraries. For instance, we can try to build the security feature as one. We can build the marketplace as another, and the compute part as a third one. So this way, we can incrementally build the entire user interface by having several Webpack configurations and compilation units. We can invoke them even in parallel so that we can take advantage of the multiple processors that we have on our machines. But in reality, the build graph of our application is not going to be that simple. We're not going to have the user interface of Google Cloud with a bunch of submodules. We may have even cycles in the dependency graph. Encoding it by hand is a little bit boring task and inaccurate. And we're usually not that good in like traversing graphs. We're not doing that like while waiting for the traffic light, let's say. So the higher level execution algorithm of a build system would be first discovering this build graph. Right after that, performing some topological sort so that we can start with the nodes of the graph which doesn't have any dependencies and which can be built independently. After that, we go to distributing the individual tasks on different computational units, which could be different cores or different machines in the cloud, synchronizing the build tasks and collecting the build artifacts. If we try to do that with the current state-of-the-art tooling again, well, this is going to be a lot of manual work that we'll have to implement by hand for each individual project that we have out there. This is going to involve a lot of custom logic in order to build a scheduler which knows how to distribute the individual compilations to different computational units. And collecting the build artifacts actually is going to be the only easy thing there. Other problems are that people with different backgrounds, they will not be able to just jump from one project to another and get productive because each project is going to have their own custom logic on building the individual production assets. But if we ignore all of this and focus, for example, on development experience, because it is a crucial part of developing a product. We cannot wait for hours our project to get compiled, or when we add a semicolon, waiting for minutes for browser refresh is not going to be the ideal user experience. We can see that, well, Webpack currently doesn't scale ideally as well. The faster the project grows, the higher the compilation time is as well. This is for a project which is about 10,000 TypeScript files with a couple of lines inside of them. And this is just an auto-generated project. So for a real-world project, this is going to be, the line there is going to be much steeper. All right, what about initial code build? By round-trip time, here I was referring to the time changing a source file and reflecting the changes in the browser. The initial code build is the time required for us to just build the project, run our production build. This is not ideal as well. Unfortunately, we can parallelize it on different cores. Webpack has this functionality as well through different plugins. And we can reuse artifacts from other builds with Webpack 5 and above. But still, this is still work in progress. Now, let us take a look at how we can achieve this with our tooling inside of Google. So first, npm install. This is something that we do not use internally. npm has some very inherited security vulnerabilities that Bill talked about earlier today. For example, last December, I believe, someone just published a package on npm, and a bunch of people started mining cryptocurrency. So it's not ideal. It's very easy to make a mistake and swipe your file system away, for example. You can just add a post-install script where you're removing a bunch of files from the user's file system. Also, maintaining a private registry is not ideal, because this way, each of your dependencies can have multiple versions. And imagine you have hundreds of projects using different versions of Angular, let's say. It's very hard to enforce a single version policy where everyone is staying on top of Angular, like on the latest version, where they can take advantage of the latest security fixes and performance improvements. So in Angular, in Google, we're using a monorepo. We have basically one directory with subdirectories, which contain the source code of different files, of different projects, or modules of the projects. This way, we do not have any inherited security vulnerabilities. If we want to introduce a third-party library that someone wants to use, let's say UI toolkit, it needs to go through a security review. We're going to vendor it if its license allows us to do that. We're going to try to sync it internally. A bunch of people are going to look at the source code and evaluate whether we can start using this. Also, we are using a lot of infrastructure. If we have only a single repository, we can have only a single CI setup. We do not have to do the same CI setups across hundreds of projects. And we can very easily enforce single version policy. Angular is just one directory inside of this monorepo. So if anyone wants to use Angular, they just need to import it from this directory. And yeah, we feel the pain. When we push a breaking version of Angular, we need to go there and fix all the projects that are using Angular, which test fails, as Steven mentioned. Now, the second part is running the build system. As Steven mentioned, we're using Bazel. This is a universal build tool, which does not understand any particular technology, but in the same time knows how to build everything. So it has very interesting pluggable architecture, where we can build tools, where we can build, rules for the individual technologies that we would want to support. So currently, Bazel has support for .NET, for JavaScript, for TypeScript, for Kotlin, for Java, and much more. Again, through different plugins. I like to call the Bazel build functional build, because Bazel has some really interesting features which are inspired from functional programming. We're going to talk about them specifically just in a little bit. But these features, because the individual Bazel, let's call them actions that it invokes, could be treated as pure functions, they can be run in parallel very easily, and we can apply memoization or caching to them, and this way improve the incremental build time of our applications. And in the same time, Bazel hasn't changed for the past over 10 years or so, which cannot be said for most of the JavaScript ecosystem nowadays. Now let us look at how Bazel works. If we put it into the context of Google Cloud Console again, and look at the directory structure of our monorepo called Google 3, we're going to see something like this here. We have Google 3 at the top, which is our monorepo. We have Angular in one of the directories. As Steven mentioned, it is in our third-party directory. We have a bunch of Angular packages, Angular material, cloud. Let us suppose that we have a B and UI directory. We have TypeScript as well. Since although TypeScript is developed by Microsoft, we have vendored it, so it stays in our third-party monorepo, in our third-party directory of our monorepo. And just Angular consumes it directly through a Bazel rule. Notice that each directory has a build file or a build.bazel file. So the build.bazel file or the build file, it basically describes a compilation unit. Each build file declares its dependencies. So the individual directories here can depend on each other. We cannot have cyclic dependencies. So if there are cyclic dependencies across several files, they need to be combined into a single package. And well, pretty much any package can depend on any other package in the same time as well. As I mentioned, the packages define compilation units. So Bazel is going to compile them independently, and it is going to recognize their dependencies so that it can build as many of them as in parallel. Here is the content of a very simple build file. Here we have two different constructs which look like Python function invocations. We have ng-module and rollup bundle. So we call this ng-module and this rollup bundle a rule. This is something that Bazel knows how to invoke and delegate its execution to other lower level tools. For example, Bazel is going to delegate the execution of this rule here to the Angular compiler and to this one here to the JavaScript bundler rollup. Each of these rules defines some inputs. These are like the arguments of a function. And also defines some dependencies. Also notice that this rule here has a name as well as this one. We can refer to the instance of a given rule by its name or by its label. It's very important that none of the rules should produce any side effects. So now we have the following situation. None of the rules produce any side effects, and all of them depend only on their inputs without any outputs. So this is inspired by functional programming. We can think of the Bazel targets as pure functions and the build artifacts as immutable data structures, which allows us to apply very powerful built-in parallel and memoization, which provides incrementality for our builds. On high level, we can discover the build graph very easily just by using Bazel query. This way, Bazel is going to traverse our directory structure, look at the build files, and figure out how the build graph of our application looks like. Here is an example of one. This is quite useful in order to review the architecture of our application, see what are the individual dependencies, and how we can optimize the build time. So this is a built-in functionality in Bazel. We can actually query the builds in order to figure out how the individual pieces fit together and how they're going to be executed in parallel. After that, Bazel is going to, of course, perform a bunch of other steps just by triggered just by running Bazel build. And on top of that, I mentioned that since the individual targets could be considered as pure functions, they could be executed in parallel and utilize all the different cores of our machine. For example, this machine here has about 12 cores, and all of them are on full capacity. So we can take full advantage of the computational power of our machines. And if they don't scale too well, we can even move our build in the cloud. Bazel provides this functionality of remote build execution that we have been using in Google for the past many years as well, where nobody actually builds the software that they're developing on their own machine. We all build our software in the cloud, and it is all running on different machines somewhere. We don't know where, but this allows us to get the fastest result from our build. In fact, by default, Bazel build is going to run the build process on our own machine as well as in the cloud, and it is going to get the fastest returned outputs. There are a couple of things that we need to consider here. The remote builds, they can take a little bit while in order to communicate with the remote server through gRPC, but in the same time, we usually prefer to combine them in our, we usually use host the build farms in our local network so that we can prevent this latency from impacting our build time. All right, so remote build execution was one of the main features of Bazel. But in the same time, once several people are working on the same feature and one of them builds it once, another team member does not have to rebuild the same targets again once they have been populated in the cache. So another big feature of Bazel is remote caching. If we build our project once in the CI, everyone in the team can take advantage of the cache which was pre-populated by the CI. So they would have to rebuild only the targets that they have modified and all the affected packages from there. This complicated diagram basically shows that we often need to have remote cache inside of our local network in order to prevent slowdowns coming from network latency. All right, so Bazel has fast initial code build because of the disk caching and remote caching and remote build execution. What about fast round trip times, or the time from saving a file to updating the user interface in our browser? Well, Bazel figures out which are the affected packages in the dependency graph and rebuilds only them and all their transitive dependencies. Here is an example. So in the previous dependency graph that we looked at, we can see that, well, again, this is a built-in functionality of Bazel. If you run Bazel query, you can output a textual representation of this chart here, which you can later convert to a PNG. So if, let's say, a developer is working on the to-do functionality, if a developer is working on the to-do functionality of our application, Bazel is going to detect that there is a change in this target based on computing the hashes of the files inside of the package. From there, it is going to check whether there are any API changes in this package. And if there are, it is going to just propagate the builds to the dependent targets of the to-do one. If there are not, it is just going to build this single package and skip the compilation of the entire application. This is how we manage to build our entire monorepo once someone pushes an update. Just Bazel computes all the affected packages and rebuilds only them. On top of that, it figures out their hashes, and if they already exist in the cache, it is going to take the built artifacts from there as well. Right. So I mentioned the level of incrementality. What about affecting the updated packages? As I mentioned, Bazel calculates the hashes for each individual package based on the files inside of it and builds a Merkle tree. Merkle tree is pretty much a tree where we have the hashes for the leaves of the tree, and each parent node takes the hash of the concatenated hashes of its children. It sounds a little bit abstract, but it is a very heavily used pattern in cryptocurrency as well. So based on this algorithm, Bazel takes advantage of incrementality and makes our build fast at scale. What about open source alternatives of the tools that we have been building our software with at Google? Well, Bazel is open source, and its release is going to be, its 1.0 release is going to be in 2 weeks. We have, you can use pretty much self-hosted remote caching, the remote caching that you can share across your organization and CI. It could be just a simple Nginx server with a couple of add-ons. You can also use Google Cloud Platform for the purpose, or even your own machine. If you want to take advantage of remote build execution, there are a bunch of build farms which are open source out there. So Uber maintains one. You can start different workers in the cloud, and Bazel is going to automatically figure out the scheduling of your build process so that it can build it in the most optimal way. Google Cloud also has some remote build execution support, which is still in a beta, so it is not public yet. But I should be able to connect you with the remote build execution team if you want to give it a try. Very often when I'm talking about Bazel, Java developers specifically, they're asking me, well, what about Gradle? We have been using it in Android for a while. Gradle is another amazing tool. There are a couple of differences between them, though. It has much less mature JavaScript support. In Google, we have a web build team, which is only responsible for improving the development experience with Bazel. It also does not have remote build execution, and there are some differences in the configuration. you can configure Bazel with a subset of Python called starlark, which is a subset of Python because we need to get some guarantees that our build eventually is going to terminate. So there are some forbidden constructs. And also, it is being executed in very highly parallel environment. So we need to make sure that we're not violating any constraints, like touching shared memory, let's say. Gradle, on the other side, is using Groovy, which is a little bit less restrictive. So there are fewer constraints with Gradle, which is easier to make your build slower. And both of them pretty much have the same performance characteristics if you do your job well. There are a couple of resources that I'll definitely recommend you to look at. We have the Angular support for Bazel, which is available at bazel.angular.io. There is an article which provides you a very easy getting started guide on Bazel with TypeScript. And the paper, the fourth link, is Build System a la carte, which compares Bazel with Make and other tools out there. It is a really fantastic article, which is a little bit more theoretical. It comes from the academia. But you can see what are the differences, and what are the pros and cons of the individual approaches in build system nowadays. Well, that's everything I had for you. I'd love to keep chatting about how we're building JavaScript at scale.